Hello everyone, and welcome to wolfSSL brings Post Quantum TLS 1.3 to STM32 Cortex-M4. My name is Anthony Hugh, and I will be presenting this recorded webinar. I invite you to follow us on Twitter at wolfSSL, as well as all our other social media platforms that we participate in. Also feel free to email us at facts@wolfssl.com if you have any additional questions. And now I'd like to give a brief company overview before we move to the technical presentation. wolfSSL was founded in 2004 by Todd Elska and Larry Stefanik when they realized there wasn't an open source dual license embedded SSL library available. OpenSSL existed at the time, but there was a demand for an alternative that was easily portable, smaller, faster, available under a clear commercial license, was equipped with a clean and modern API, and offered commercial-style developer support. wolfSSL was born into this market need with an OpenSSL compatibility layer. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of almost 50 dedicated employees in 2022, most of which are engineers. This progress is of course supported by a strong partner network that we're very proud of, which includes DDCI, STMicro, and RTI, just to name a few. Since the beginning, our engineering team has developed several embedded security products, including wolfcrypt with DO178 support, FIPS certification, and a FIPS-ready offering. There's also MQTT with up to the v5 specification. We have SSH-v2, TPM 2.0, a secure bootloader known as wolfboot, as well as Java wrappers and JSSE support, and commercial support for curl as well. All of these offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now, I'd like to jump into the STM32 Cube IDE. Okay, so here we are in the STM32 Cube IDE. I've created a project called wolfSSL underscore STM32 underscore PQ. And let's go into some of the configurations in the IOC file. The most important configuration here is the software pack, wolfSSL. Note that the version here is a little bit strange. It's 8.8.8. There's obviously no such version of wolfSSL. This is a special kind of thing that I had to create on my own as I had to make a pre-release to kind of make sure that this worked. Okay, so here we have the PQM4 Post Quantum Integration support. This is, of course, not enabled by default. We have to enable it now. And it's, of course, not available in the current release of wolfSSL that you can get from the STM32 Cube IDE pack tool. So the currently available version is 5.2.0. Once 5.3.0 becomes available, this particular feature will be there. And again, it's not enabled by default. If it becomes enabled, then wolfSSL expects certain files in the project that are from the PQM4 project. We'll get into those files later. Another interesting setting is the math configuration. This particular setting is was changed to the single precision assembly optimized assembly optimizations for Cortex-M3 Plus. This is an M4, so this applies. And you know, for post-quantum crypto, this isn't really important, except that if you want to do comparisons for benchmarking, then these numbers, then this particular setting is important because you want to get a fair comparison. And this particular setting gives the best numbers for the conventional algorithms such as ECC. Okay, so let's go into some of the other settings that need to be changed. In connectivity, USART 2 is normally disabled. I have enabled it here into normal asynchronous mode. The GPIO settings are by default PA2 and PA3, but if you set them to PD5 and PD6, they're right beside each other, and then you can, when you go to use your TTL cable, you can just plug it in. You don't need to use any kind of jumpers or any kind of cables like that. At the end of the presentation, I'll show you a picture of my board and how I have it plugged in. Okay, so if we look at the NVIC settings, we want to turn on USART2 global interrupts. This is off by default. And in DMA settings, we want to, let's go into this for detail, we want to do a USART2 RX DMA request. Everything else, once that's set, is normal. All of these are the defaults down here. Okay, so I'll just close that up. Or sorry, I'll move on to the next thing I'd like to show you in here. And that is turning on the RTC. So let's see, is it here? Oh, no, I think that's the timers. So the RTC is an active clock source. Activate clock source is checked. That's normally off by default, but we turned it on. That's just because we need it for the benchmarks, I believe. So I should go into a bit more detail as to what I was talking about with the USART2. So we're doing DMA requests. We're using DMA for USART2 because we're taking in TLS 1.3 data over the USART. Now, when we receive it, we receive it via DMA because we don't know how big the packets are. And if we don't know how big they are beforehand, we kind of have to use DMA read to idle. And that's basically the only choice when it comes to dynamic data sizes. And so that's why we're going to the trouble of doing these DMA settings. Okay, that closes it up for the IOC file. Okay, so as you might have noticed, there's a bit of lack of continuity at this point in the video because, well, we've changed the theme of the IDE, and the reason why is because the way it was set before, it made it really hard to read the text. So I wanted to make it easier on your eyes, so I've changed the theme so that it's easier to read source code under this theme. Okay, so now I'm going to go into some of the code that I had to write to make this example work. So, of course, there's new code after closing the IOC. A lot of it's generated, for example, with the UART2 being enabled, a lot of code gets added into main.c. As well over here, this wolfSSL gets generated, this file gets generated. In the middlewares, third party, here, this wolfSSL directory gets populated with the entire wolfSSL library. And I'd like to show you the source main.c file. I'll show you some code that I had to add. And if we search for demo, here we're declaring the wolfcrit demo function. When you call in here, it will activate the demo code for wolfSSL. And the next function is here, which is the actual execution of the wolfcrit demo. And this is done between user code begin2 and user code n2. And this is inside the main function after most of all the other cube IDE initializations are done. And this is also just before the main user while loop, so you will never get to the user while loop. Some other things that we had to do was to add these functions. I'm not exactly sure why this has to be done. All I know is in order to properly support printf and printing standard input, standard error, and standard in, this needs to be done. As well, there's some code above which also needs to be done here. So there's this user code begin PV, and then there's this user code npv. This code in between must be added, and this just helps printf effectively be used properly, work properly. Okay, now I'd like to also show some changes that I had to make to this particular generated file, middlewares. Nope, not this one, sorry. The wolfSSL. This directory is generated, and this file is generated. Let's see. All of these are settings that you normally set in the IOC file, like this one right here. I had to go to the end of this section, and for this particular platform, we define wolfSSL STM32 F4. We set the HAL console UART to whoart3, or HUART3, because that is the default for this board. And if you look in the IOC file, you'll notice that UART3 is already enabled by default, and it leads to the debug USB port. There's no STM32 RNG, and so what happens is a kind of fake seed is used. You'll notice when we build, you'll notice some warnings coming up, and we'll have that as well. There's no cryptographic acceleration on this board, and we are not using HAL v2. Okay. That's it for this file. And for main.c, that's all. Okay, so now I'd like to talk about some of the files that we had to bring in from the mupq project. They have several repositories. There's pqclean, there's pqm4, and then there's also an mupq repository. So all of the files came in, are in the include, which is here. These are can be thought of as API headers, api_kyber.h and params.h, and this particular directory, which is has all the files that we brought in from those repos. I'm going to go into where they came from, and I have a few slides and diagrams as to what I had to do with these particular with these particular files. Okay, let's see. So here we are. So as you can see on the right, we have a representation of the wolfSSL underscore STM32 underscore PQ project. It's got all the standard directories. I haven't shown all of them, but it's basically a typical project. With an extra directory added, I created the PQM4 underscore Kyber directory. And so inside the core include directory, we added api.h and params.h. And these basically are specifying that we're using Kyber 512. And that's what we know, what we call in our system, Kyber underscore level 1. Now here's a list of files that we brought over from the PQM4 repository. I'm not gonna, I mean, they're listed right here, so I'm not gonna go into too much detail, but they were just basically copied over. No modifications were made in these files. So yeah, from the mupq repo, we took the Kachak F1600 implementation, as well as FIPS 202. And from pqclean, we took their randombytes.c. Now, randombytes.c did get modified, just so that we could have we could support a platform that didn't have a random number generator. And again, it has, well, I'll show you the modification in a moment. We renamed api.h to api underscore kyber.h. This is just, you know, just in case someone, in case we want to use another algorithm in the future, we'll use, it's better to specify the algorithm name in the header file name. So we were finding that poly.s as well as matacc.s had conflicting file names because they had .c file names that were exactly the same. So when builds came along, for example, poly.s would be compiled into poly.o, but poly.c would also be compiled into poly.o, so there would be, you know, file name conflicts. So we just renamed them, and we literally put, we literally appended underscore renamed to their file names, and then everything was fine. Okay, so let's get back to the IDE. As promised, I'm going to show you the random bytes change. Where are they? There we go. Random bytes is here at the very end. Let's get to the end. There we go. Whoa. There we go. So if you look at all these platforms, it goes through each one to see, and you know, at the end there's a warning: random bytes is not supported on this platform. And so what we do is we generate a buffer with just a bunch of with incremented numbers in it, and that's it. Now this is not a good practice for production. Obviously, you should never do this in production. But again, for, you know, for the sake of testing, this is what we do. Okay, so that just about wraps it up for random bytes C. Now, the next thing I want to get into is some of the build and project settings that we had to kind of set up. So, of particular note, we are building in release mode, and in our run configurations, we are specifically setting it up so that we are taking the release version of the ELF build product. Okay, and to show you, yes, in our project settings, we are going to be running benchmarks. As such, we are going to need to display some floating point numbers. So we'll go in here, go to C++ build. Let's see. Build variables, no. Settings, there we go. I believe we're going into the MCU GCC compiler, looking at general. Oh, geez, is it assembler or compiler? General. This always takes a little bit of time because there's so many options. Or is it MCU settings? Hold on. There we go, MCU settings. So in the MCU settings, we're going to use float with printf. And if you this is off by default, but if you click it on, you'll be able to display floating point numbers. Okay, apply and close. We didn't change anything, so it doesn't matter that we apply and close. Now there's one little quirk with the PQM4 code, and it's that if you have optimizations turned on, then you're going to it's got problems with optimizations turned on. So I've already contacted people at the PQM4 project and let them understand this problem. But to mitigate it for now, what we do is we turn off optimizations in release mode for all the PQM4 files. And include path, GCC compiler, yes. Optimizations, there it is. And normally it would be set to OS, but we set it to -00, which means no optimizations, none. Okay. And we don't change anything, so it doesn't matter. Okay, so it's finally time to do a build and an execution of the demos, and maybe run some benchmarks as well. First step is to clean the build, just so that you can see how long it takes to build everything together. It's not long at all. wolfSSL is a fairly small, is a large project, but it can build quite efficiently. So we're going to do a clean project. Okay, the project's clean. Now we're going to do a build here. Remember now that we are doing a release build, so I'm going to click that little hammer there. You can see down here that a lot of building is going on, a lot of text is flying by. We've got a couple warnings. Let's see what this warning's about. Ah, right, yes, it's like I showed you earlier. The random bytes is not real. We wanted to make sure that this warning appears during the build to remind people, you know, this is okay for testing, but this is not a real random number generator, and they should know not to put this into production. Okay, so that's been built. Let's deploy it to the STM32 board. So we'll click that, and then we will. Oh, okay. So it's showing that the board was reboot, but in the middle of its reboot, it was stopped by the debugger because it's flashing now. Okay, so everything's flashed over. We're all good to go. Now we'll minimize this, and as you can see, I'm in the wolfSSL examples repo. I've got in that repo, I'm in the PQ STM32 directory. PQ/STM32, excuse me. And let's see if I do an ls, this is what we have. So you'll also notice that wolfSSL STM32 PQ is here. It's not going to be exactly the same as what you've seen me working with up till now. What's there is going to be the same project, except it won't have wolfSSL imported into it already. And that's of course because it's not going to be in STM32 cube. Um, the pack tool. It won't be in the pack tool until 5.3.0 of wolfSSL is released. Okay, so just understand that, and understand that you'll have to wait for 5.3.0, and you'll have to reconfigure in the IOC file to enable SPMath and enable the PQ-M4 integration, like I showed earlier. Okay, so let's build the Linux PC side server and client for UART. Okay, that was pretty easy, pretty simple. That's because wolfSSL has already been built and installed. Let's see now. So that's done. So let's make the PC the server first. So sudo. You'll need sudo because it's accessing the UART through TTL, and the TTL is seen by Linux as a USB serial device, and therefore you're going to need sudo access to access that device. So sudo /server and push enter. Yeah, it's looking for my password. Okay, so it's waiting for the client, and we're going to look for, and now on this side over here, on the STM32 board side, we are going to press C to run the client. Look at that. Both sides had a successful connection. Okay, now let's try it the other way around, where the STM32 board is the server. And we're just going to change the server to client. Look at that. On this side, we have success. And on this side, we also have success. Note, just to make sure that you that the user knows, we are using Kyber level 1. Okay. Now, interestingly, if this is built without libOQS integration, if wolfSSL is built without libOQS integration, it will just go back to the default normal TLS 1.3 cipher suites with the default normal groups. Okay, now that we have, and if it does do that, it will tell you that it's using a normal TLS 1.3 group instead of Kyber level 1. Okay, so now that we've seen the server and client, the TLS 1.3 connections in both directions, I'm going to run the benchmarks on the STM32 board. So here we go. So it's running through all the conventional algorithms first, and at the very end, it will show us the Kyber level 1 results. Okay, and here we are. We have 62 keygens and 28 encapsulation, decapsulation cycles. Now those numbers aren't bad. They're not bad at all. But they are actually typically much higher when optimizations are turned on. And so once the PQ-M4 project has a fix for the problem I said, the problem I reported to them, we'll get that patched in, and then we will have better results. Okay, so now that the demo's over, I just want to have a few quick words about the actual platform, the microcontroller. We did this on a Nucleo F446ZE platform. It's got an M4 chip on it. And this, what you're looking at right now, is the top view of it. I kind of got it from a weird angle, so you can't see any of the pin labels on the outsides, but that's the top view. You can see the cable coming out of the bottom, and that's because the TTL cable connects to the pins on the bottom and not on the headers at the top. And this view is the same view as before, just rotated 180 degrees along the vertical axis. So you can see that what would have been on the left is now on the right, and what would have been on the right is now on the left. You can see that the TTL interface is plugged in, and it's plugged in a kind of a strange configured way because it's straddling both two different headers if you're looking at it from the other side. But it just seems it's how it works, so it's doing really good this way. Another thing that's really great about this board, and something that really kind of makes it shine, is the cost. Like, the reason why people might want to see post quantum cryptography on an M4 is because this whole entire board with all these little components and breakouts and things, it's listed on Mouser.com for less than $20 US. Sorry, less than $20 US. So you could get, a whole microcontroller for under $20. I don't know how much the microcontroller individually is, but this board is less than $20. I mean, that's incredible. And, it can do post-quantum cryptography. So, if cost is a factor, then maybe let's talk. Like, please get in contact with wolfSSL. So here are some links for things that are related to what you've just seen. The first link is, of course, a link to the blog post announcing that we've achieved TLS 1.3 key establishment on an STM32 Cortex-M4 board. The second link is a link to the samples that we just ran in the demos. The third link is a link on how to build and configure STM32Q projects on with wolfSSL. It basically goes into a lot more detail and a lot more text that regarding all the things that I showed in the video. The fourth link is a link to the GitHub repo for the mupq team, and there you'll find the various projects where I got the code from. And finally, the final link is an issue report to the mupq team regarding PQM4 not being able to be built in release mode because of optimizations, and you can monitor the progress there if you'd like. Thank you for listening this far. This is quite a long presentation, I know, so I'm really thankful for anyone who's listened this far. If you have any further questions, please contact us at fax@wolfSSL.com. Have a nice day now.